Thank you very much for inviting me, Ganesan. I'm in St. Louis, and supercomputing is going on well. Lots of technical sessions and exhibition floor talks and other activities, as you would imagine. I have, thank you for inviting me for this ADG session. I have put my slides over here for everyone. I hope you can see my screen properly.
Yes, it looks good.
Okay, great.
Any important thing you observed as part of the SC21?
Well, they have the OpenCAPI booth, and they are showing modules of how OMI can be used with the systems. That was interesting to actually see the OMI boards over there and the memory modules and all. So exciting. We look forward to how we can try the Power 10 systems in the future.
Thank you.
So the two key challenges that we are trying to address here are that with this growing complexity of our hardware, it is now getting harder to accurately measure and optimize the performance of our HPC and AI/ML workloads. And the second challenge is that as our software packages become more complex, it's even getting harder to install the tools and libraries correctly in an integrated software stack. And to address these two challenges, I would like to share the work that's going on to improve productivity of programmers using the TAU performance system, which aims to deliver a scalable, portable performance evaluation toolkit that not only applies to HPC, but also to AI and ML workloads. And the second project, which includes TAU, is the extreme scale scientific software stack. And here, our team is delivering a modular, interoperable, deployable software stack that works across different architectures and platforms. And it lowers the barriers. It lowers the barriers of using software technology products from the Exascale Computing project and other E4S products. And where possible, we are trying to enable uniform APIs for interoperability. And you can learn more about these two projects on these two websites. So the TAU performance system has three main components: the instrumentation layer, where you add hooks to your program. These hooks can be inserted at the source level, at the compiler level. You can even wrap libraries like MPI, and you can also spawn the applications using a special tool where you can operate on an unmodified binary. It aims to support all the HPC platforms, compilers, and runtimes that are relevant to us. And once you add these hooks, they then internally call the measurement code, which can create profiles or traces. And then you can analyze this performance data using tools such as ParaProf that ship with TAU, or third-party tools such as Vampire as well. We support a large number of languages and runtimes, and these include Python, C++, Fortran, even other HPC languages like UPC and Chapel. And we have support for automatic instrumentation and support for many different runtimes, including MPI, PGAS runtimes, even GPU runtimes like CUDA and OpenCL. And then we have support for parallel performance analysis using ParaProf and Perfect Explorer. So in case you're wondering, how does TAU help me? Well, it can tell you how much time is being spent in different code regions of your application, at the loop level, at the routine level, even at the statement level. You can see which kernels are executing on GPUs on machines such as Summit at Oak Ridge, and you can see how much time it takes to transfer the data between host and device. Instead of time, you can measure hardware performance counters, such as floating point instructions, level 1, level 2 data cache misses. You can see the memory usage of your code. What is the memory footprint of your application? And by the footprint, I mean the total of the stack, heap, data, text, DSS, the full image of your process, and what is the max high water mark of the total memory used in each process. You can see the energy usage, you can see the IO characteristics, you can even see how your application scales across different core counts. But to do all this, you need to add hooks to your code. And the instrumentation phase can be done at the source level using a preprocessor such as PDT, or by the compiler, which can add hooks to your code. Both client compilers, GCC compilers, as well as the IBM Excel compilers have these flags that TAU compiler scripts, such as TAU-cc.sh or TAU-cxx.sh can call. You can also launch the code unmodified using MPI run with a TAU exec and then the application. So this TAU exec tool can preload TAU's dynamic shared object while running your code and then generate profiles or traces. Now, while profiles show you aggregate data, traces can show you time varying data or show you the temporal aspect of your code, which shows you what each process was doing at any point in time along a timeline view like this. And using this TAU exec tool, you can intercept the runtimes at MPI level, OpenMP level. You can also check all the other options of TAU, such as looking at the communication matrix or generating OTF2 traces, or even enabling open, event-based sampling in your code. And here's a quick start guide. You load the TAU module or set it in your path. Then you can launch your code with a TAU exec with the event-based sampling flag like this. So this is an unmodified binary. You just launch it with MPI. If you have a OpenMP code, say using the Clang compilers, you can turn on the OpenMP tools interface and view the data using the OMPT flag, or with pthread, or use TAU Python instead of Python to get detailed information at the Python level, or get data at the CUDA profiling tools interface level, CUDA. Here is the profile browser that you will launch after you generate the performance data. ParaProf will show you what each MPI rank is doing and which functions or code regions were using how much time. If you just stack these bars separately, you will see each function in its own color space over here. You can also see a thread statistics table, and you can also see the event charts in TAU. Here you are seeing the time spent in a given kernel in a code called XIFEL, which was run on Summit. And then you can see the options of -kupti, which extracts the kernel name running on the GPU, and you can see which kernel took how much time. You can also see inside that kernel in Python and see exactly which code regions took how long with how many samples that were collected. You can look at the inclusive, exclusive time, and when you expand this, you can see which line in code is taking how much time. So you can go right down to the source code by clicking on a line like this. Or the context event window will show you the extent of variation of a particular event, whether it is the data copy from the host to the device or IO activities along a particular calling chain. You can see the context event window. And you can also peek inside the MPI libraries. That's right, you can look inside what happens inside the Spectrum MPI library, and you can see how this is the bcast operation that's calling the PAMI context lock or pthread spin lock. So it allows you to get a detailed view of even vendor libraries. Now, you may not have access to their source code, but it will show you things like there was a device InfiniBand IB verbs device advance function, and that was taking 1.5 seconds in the bcast operation. So you can peek inside the MPI libraries, and would like to thank IBM for keeping these symbol names, which really helps the tools like TAU. And you can even unwind a given call stack, and you can see exactly who called a particular function, and look at detailed information by sampling and seeing how much time was spent in condition wait using the TAU Python, and see the events occurring on the GPU side. This is event-based sampling with just a stock binary without any modifications. And you can see the exact line number and how much time was spent in that line across different code regions. With Callsite profiling, you can also check a particular function and where it was called. Like if MPI receive was taking 14.6 seconds, you can now see with Callsite instrumentation that when the receive function was called in exchange one function at exchange1.f at line 68, it took 12.6 seconds. And when the same function was called at a different line like 86, it took 2 seconds. So you can look at a given call site for an instrumented function and see the contribution of that. This is the context event window that shows you along a calling chain how much I/O was performed by read-write bandwidth and bytes written. We even have a 3D profile browser that you can see with the function names, the MPI ranks, and the time it takes. You can also use the crossbars to zoom into a particular location. And the same goes for communication windows in TAU, or the trace browser that ships with TAU, which is Jumpshot from the Argonne National Labs, where you can see a timeline view with all the processes. TAU also supports Perfetto and Chrome browsers, which are probably already installed on your laptop. And all you need to do is turn on these flags and then launch the application and then merge the traces and convert them to a JSON file and load it in the Chrome tracing. We recommend the Vampire Trace browser, which is a commercial grade browser from TU Dresden, and TAU supports the Cocos profiling interface. So you can generate detailed node level profiles which have the detailed Cocos kernel names as specified by the user that appear here instead of mangled or demangled C++ names. TAU has support for many different runtimes. We have support for MPI with both PMPI and MPI-T, pthread, OpenMP, OpenACC, OpenCL, CUDA, ROCm, Cocos, and even Python. And you can mix and match these runtimes, such as you have Cocos with pthread backend with MPI library, or Python with CUDA and MPI for launching TensorFlow or PyTorch with MPI. And this is how you launch the application. If it's uninstrumented like this, then you can just turn on one of the runtime options with TAU exec, and you can just enable this. And with the -t parameter, you can specify a tag, such as this is an OpenMP OMPT configuration with MPI. And you can turn on memory tracking, you can turn on event-based sampling, even specify the resolution at the file, function, or line level. But how do you use TAU in the context of a full software stack? How do you install this package? Well, one of the projects we are working on is the extreme scale scientific software stack, which aims to deliver a high quality and robust software products and create a whole software stack. This is a project from the ECP Software Technology area. And there are many different technical areas within that, going from programming models and runtime, and the software development kit of that, which I lead as the SDK lead on the PMR, to the development tools, math libraries, workflows, data and visualization, NNSA, ST, and also the full software ecosystem area. And the goal here is to create better products, have better documentation for the E4S products, and have a comprehensive portfolio of testing, quarterly releases. And we just did a release of 21.11 for the November 2021 release. And it's a curated collection that hopes to simplify software installation, and with the help of build caches, improve the time for deployment of the software. And you can find out more about it at the E4S.io webpage. So as I mentioned, it's a curated software distribution based on the Stack Package Manager. And we have binary build caches for bare metal installs, as well as container-based deployment for multiple platforms, including PPC64LE. And we have container images on Docker Hub, as well as E4S. We have base images, which you can use to cherry pick these packages and just install what you need to create a customized, optimized distribution, which is compact. Or we have full featured containers with GPU support, of many different packages and GitHub recipes, integration with continuous integration frameworks with GitLab, even a validation test suite to make sure that everything works correctly when it's installed. There are AWS and VirtualBox images as well. And starting from our first release in October 2018, we've come a long way. In this conference at SC, we released the E4S 21.11, which has 91 full release products, and also products like PyTorch and TensorFlow, AI products targeting the NVIDIA GPUs that work with the PPC64LE image. There are also other co-design products like MRX, Kibana, MFEM. And here is the download page where you can see the software stack, and it's available as Docker containers, Singularity containers with base images. So you can see the base image for PPC64LE for GPU-based images. We have the Docker Hub image, which shows you the E4S GPU, and you can just run a command like this with pulling the image, and then with Docker you can launch it like this, and then it will run your image. Here are the 91 E4S products that are deployed, and we support NVIDIA CUDA 11.0 as well as NVHPC 21.9, which has multiple CUDA and compilers and OpenMPI in this. So you can see these are products like Amrex. You can see Feudel. We have HDF5, Cocos, MPage. We have products like OpenMPI. These are products that you use on a daily basis for doing HPC computations. We have TAU and Trilinos also in this distribution. We have a support for AWS, and we have multi-platform reproducible Docker recipes. This is for PPC64LE for UBI 7. What is interesting about UBI is that with this universal binary interface Docker image, that if you are running Red Hat Enterprise Linux on your IBM system and you use a UBI-based image, then that image is supported. And whatever happens with that image is supported with the Red Hat model. So that's a very compelling reason to use the UBI images for Red Hat systems. We also have support for bare metal installation. So you can just use this recipe of SPAC and just download SPAC and install the packages. Here are the instructions for bare metal installation. You just have to say, this is my environment in the current directory -e dot, and then say SPAC -e dot install. And you can also build with this recipe a Docker-based container, and you can specify this argument. Here are the runner images for IBM Power 9 systems, the PPC64LE systems. We run these on a range of open power systems, from Raptor to IBM IC922 to AC922s. And the E4S community policies are available on our web page as well. You can refer to these policies to become a member product in E4S, and they're based on the XSDK policy. So in summary, what I would like to say is that E4S is not just a closed system that only takes contributions from DOE software development teams. You should think of E4S as an extensible open architecture software ecosystem that does accept contributions from US as well as international teams. You should think of E4S as a framework for collaborative open source product integration and a full collection of compatible software capabilities and a manifest of a la carte selectable software capabilities, a vehicle for delivering high quality reusable software products, and a conduit. I think of E4S as a conduit for future leading edge HPC software targeting the next generation scalable computing platforms. Much of the research is carried out at the Performance Research Laboratory that I direct at the University of Oregon. This is our campus in Eugene, Oregon. And I would like to thank the Exascale Computing Project for their sponsorship of TAU and E4S. And I would like to thank all our collaborators in the ECP and the broader computational science communities who have worked closely with us to deliver this software stack and the performance evaluation tools. With this, I'll take any questions.
Dr. Sameer, thank you for the wonderful presentation about E4S and TAU, the performance monitor. Our team, the participants and panelists, do you have any questions for Sameer?
Well, I have put my slides in the chat window. I hope you can download those, have a look at those, and feel free to ask me questions offline too. And here is my email address as well, if you would like to reach out to me offline or set up some time to meet at SC as well. I'm here for the next couple of days. And with this, I hope we'll be able to get back on track with our schedule for ADG.
Yeah, thank you. Thank you, Sameer. Thank you very much.
And thank you, Prateek.
Yeah, thank you. And let's, audience, I mean, participants and the panelists, let's move on to the next presentation.